Hello, everyone. Let's get started with today's lecture. Today we will continue the discussion that we started last week, namely exploring this probabilistic and statistical perspective on supervised learning. Right, and so just to remind everyone, what we've done in the last lectures is we've taken our optimization-centric viewpoint of supervised learning, namely the problem of optimizing over a family of hypotheses or functions, the one that minimizes the loss on our training data set, possibly up to some regularization. And we've seen how we can take this family of learning approaches and view them as the problem of essentially trying to solve a parameter estimation problem in a certain statistical model. Right? And we concretely worked this out in the case of regression. In particular, we started with least squares, linear regression. And we've seen that finding the least squares fit is equivalent to doing maximum likelihood estimation under the particular assumption that our noise is Gaussian. Right? That basically for a given x, the observed label y is just W transpose X plus some Gaussian noise. Okay? Now this is useful for 2 points of view. First of all, it's sort of can now be used to actually try to model the uncertainty in the prediction, right? We now make an explicit assumption, right, that our noise is Gaussian distributed, which allows us to maybe quantify the uncertainty in the prediction. And it also provides this very natural viewpoint of exchanging one particular noise model for other noise models. And similarly, we've seen how regularization, in particular rich regression, right, penalizing the sum of squared weights, is nothing but being Bayesian about the weights, right? Putting a Gaussian prior on the weights, and then instead of doing maximum likelihood estimation, we would do maximum a posteriori or map estimation for a parameter vector, right? This is what we've derived. So rich regression, which is motivated from this pure optimization point of view, corresponds to finding the parameters that are most likely a posteriori given a Gaussian prior on our weights and assuming Gaussian noise in the labels. Right? And what we already started to explore in last lecture is to now how to swap these different components. Right? So if you swap the Gaussian prior in our weights, we can put in a different prior of our weights. Right? If you plug in the Laplace prior, we get the Lasso, but we could plug in other priors as well. Similarly, if you don't really believe our noise is Gaussian, we can plug in a different noise model, right? Say a student T noise model, for example, right? That would capture the assumption that maybe our noise is more heavy-tailed than a Gaussian noise. Okay, so this is a very natural point of view, right? And then essentially through this lens of maximum posteriori estimation, this leads to a natural optimization problem, which we can then try to solve. Okay, so last lectures we focused on regression and just started to talk about classification, which is what I want to continue in today's discussion. Right, how this perspective is useful for classification. In particular, what we've introduced in the last lecture is an extremely widely used model for classification, namely logistic regression. And here the idea is that we basically try to model not the class label itself, but the class probability. Right? So the idea is basically to sort of view classification as a regression problem, but replace the assumption that our noise is Gaussian by a different likelihood function, right? By the assumption that our noise is now a coin flip, right? A Bernoulli distribution, right? And what we now model is the bias of that coin flip, right? The probability of the positive or negative class, right? So this is what we set up in the last lecture, right? So instead of assuming the conditional distribution of y given w and x being a Gaussian distribution centered at W transpose X, we now assume it's a Bernoulli distribution, right? So distribution over binary outcomes with bias, right? Probability of heads being given by sigma of W transpose X, and sigma is just this logistic function, right? So we take our continuous valued response, W transpose X, which is ranges over all, the entire reals, and now we map this to a value between 0 and 1 by squashing it through the sigmoid function. right? That's the same kind of sigmoid function that you've seen in the context of neural networks as well as an activation function, right? But here it's really part of the likelihood. Okay, so now this, right, this essentially you can view it as derived from linear regression, right? But replacing the Gaussian noise with Bernoulli noise. Right, so here's just this logistic function once more that we had talked about. Right, and now this is basically a modeling assumption, right? We swapped this Gaussian noise model and replaced it by this Bernoulli noise model. It's more tailored to classification, right? Because we only have discrete labels, right? And so now the question is, how do we go about parameter estimation? And of course, we can open up our toolbox that we have discussed before, right? We can do maximum likelihood estimation, or we could think about putting a prior on our weights as well and doing maximum a posteriori estimation on the parameters. Right, so let's start with maximum likelihood estimation and just work through what this gives us and what the resulting algorithm looks like. Okay, so let's do it. So basically, what's the task? Well, you want to estimate W hat in the argmax of the probability of our labels, right, y1 through n, given W and the x's, right? We maximize the conditional likelihood. That's the same exact thing that we had done for linear regression, if you remember, right? And we optimize, of course, over W's. Okay, and now what we do, well, obviously, this is the same. Right? We use the usual trick, right, that we always apply when doing maximum likelihood estimation, right? Maximizing the likelihood is the same as maximizing the log likelihood, which is the same as minimizing the negative log likelihood, all right? So this is the same as the argmin of minus log p, purely by monotonicity, right, of y1 through n, given w, x1 through n, right? And now the other thing we need to do is, again, invoke our independence assumption, right? The independence assumption that the noise is independent. Right? The noise is independent across our data points. Right? You have conditionally independent noise, so that's the argmin over all w's minus the log, right? And this independence assumption, this is going to factorize as the product over all data points of yi given xi and w, right? And then the log of a product is going to be the sum of the logs, right? The same as we had seen before, right? So this is the same as minus the sum over I equals 1 up to n of log p of yi given w and xi. Right? So this is independent noise. Right? So that's the assumption that we invoke here, right? And now the only thing that's left is to sort of work out what this boils down to, right? So if you compute this log probability here, so let's draw a line, right? And let's plug in the definition of p of y given w and x, and look at the negative log of that, right? So negative log of p of y given w and x is minus log of what? Well, this is just 1 over 1 plus e to the minus w transpose x. It's just a definition, right, of this conditional probability of the label. Right, and now that simplifies, of course, right? I have the log of this fraction, right? So this is just going to be minus the denominator of this fraction, right? And then the minus is going to cancel with the minus in front, right? So this is just basically, so log of the fraction is minus the log of the inverse, right? So, and then the minuses are going to cancel. So this is just log of 1 plus e to the minus w transpose x, times y. right? So the minuses are gone, this fraction is gone, and then of course plugging this in, right? So this is star is basically just the argmin over the w's of sum over I equals 1 through n of log 1 plus e to the minus y times w transpose x, and the I is of course, right? Because this is the ith data point, okay? And so now this looks very familiar, right? It's again the sum of losses. A mistake, yeah? What happened? Oh, there's a y missing here. Is this one? No? Okay, thanks. Good. Okay, so is this clear, right? So this is basically now this very familiar form, right? That we have a cost function, an empirical risk, right? That's just the sum of losses, one per each data point, right? And let me actually, okay, this is fine, right? And so now essentially this in here is now just a different loss, right? And so this is called the logistic loss. Okay, so it looks very similar to what we had before, right? This is this cost function. And right, similarly to many other losses we've seen, this is a convex loss. I'm going to show you a plot in a slide, right? So it means, again, we have a sum of convex functions. So the function r hat, this empirical risk is again convex. And we can use convex optimization in order to find the optimal W. Okay, so this is very much in line of what you've seen throughout this class. So here's the plot. All right, so 3 plots. The red one, again, is our 0-1 loss. So arguably, I mean, a very natural loss for classification, right? Counting the number of mistakes. The blue one, what's the blue one? That's the hinge loss, right? The upper bound on the 0-1 loss. So this is the hinge loss. And this green one, the new one here, this is the logistic loss. All right? And so just to describe this a little bit, right? So if we look at the function, just spell this out here, L of Z is log of 1 plus Z, right? So the logistical loss is just this function here applied to Z equals minus y times double transpose x, right? Then this basically is approximately equal to Z for large Z. And approximately equal to 0 for small z, right? As z goes to minus infinity, right? And so this behaves roughly, so it's similar in some way, right, to this max function here, max of 0 and z. Okay, it's sort of a smooth approximation to this kind of function that you've seen many times, right? So in the context of neural nets, this was our value function, right? And in the context of the perceptron, that was the perceptron loss, right? And you can view this as sort of a smooth approximation of this particular kind of nonlinearity. Okay, that behaves the same in the limit. Yeah? Once again? Yeah, sorry, thanks. E to the set. Okay, right, so this is the same for z equals, so in logistic regression, z is minus y times double transpose x, right? Okay. It's very similar to things that you've seen already. And now, right, that means, right, so we have a convex problem, right? Even now is nice, smooth, differentiable, and so on, right? So it certainly is natural to do gradient-based optimization. So let's try to work out the gradient of this cost function. And turns out that also has a very nice form. And so again, right, in the end, what we're going to do is some form of stochastic gradient descent. So what matters most to us, as throughout this lecture, is the gradient of the loss with respect to a particular data point xy, right? So this is the loss function spelled out here, right, the logistic loss. And so let's compute the gradient of W. Okay, and of course this is again vector calculus, right? But but I'll just work it out, right? So we differentiate this with respect to W. So we have, of course, we have to apply the chain rule, right? So there's the log outside, and so differentiating that will give us something that's 1 over the argument, right? So we'll have 1 over applying the chain rule, right? 1 over 1 plus e to the minus y times W transpose x, right? And now we have to apply the differentiate with respect to the argument, right? The argument is 1 plus e to the minus y times W transpose x, and computing the gradient with respect to W. So the constant 1 doesn't matter, right? And the 1 plus doesn't matter. And now we have to apply to the exponential function, right? So we'll get the exponential function back. So we'll have e to the minus y times W transpose x. And then have to apply the chain rule once more, right? To differentiate with respect to the argument of the exponential function. And that gives us, right, with respect to W, just gives us minus y times x. Okay, that's it. So that's the gradient. And you can simplify it a little bit. So let's notice 2 things here, right? So okay, so let's just spell it out, right? So x of minus y W transpose x divided by 1 plus the same thing, right? So we note that these are the same, right? So this term and this is the same, right? And now what we can do is we can just divide by this quantity, both the numerator and the denominator. Let's do minus y times x here, right? We still have this. Okay, and so now this here just is the same as 1 plus, okay, let me write it like this, e to the y times W transpose x plus 1, right? Times minus yx. Right, what did I do? So I just divided the numerator and denominator both by e to the minus y times W transpose x, right? So then I subtracted from the argument of the exponential function in both cases. So this goes to 0, so e to the 0 is 1, right? And then here we now have this, right? Okay, times minus y times x. And now we are almost done, so we can just give this a nice interpretation. So what is this loss function? Can you recognize this term here? Does anyone recognize what this term is? With respect to our model, has a nice interpretation in terms of the model, right? So this is just the probability that we attach to the negative label, right, to the flipped label, right? So this is just p hat, right, of y equals minus y given W transpose in x. Okay? So let's stare at this for a little bit and try to get an idea about the gradient. So basically what is the gradient, right? So let's just write this down here, right? So this is p hat of y equals minus y W transpose x times minus y and x, okay? So the first is a scalar, it's just a number, in particular a number between 0 and 1, right? It's a probability. And the second argument is a vector, right? That the vector gives us direction. Okay, so what's the direction of descent Well, it's minus y times x. So that's the same descent direction we've seen many times before, right? The same update direction in the context of least squares, right? The square loss, direction in the context of the hinge loss, etc., right? Because essentially all of these losses are ultimately a function of y times w transpose x. So this shouldn't be surprising, right? So the descent direction is again in the direction of our data, right? If you take a negative gradient direction, we're going to update our weights a little bit in the direction of the data point, of the current data point. Now the question is, how far do we update, right? And this is given by the coefficient in front, right? And this coefficient in front here, right, basically says the following, right? So if our model attaches a very high probability So what does this mean here? When is this large? Well, this is large here if what happens? So if a model says is very confident about y being little y, right? The label of the current data point. Right? So, sorry, if our model is okay, so when is this large? So it's large basically if this quantity is big, right? So basically if the model says under the current model parameters, okay, sorry, it's a comma here, right? So given our current model, it says that y equals little y, right? The actual observed label. If that is small, right, then this number is large, right? So essentially, if the model is surprised by the current label, right? So if the model attaches a very small probability to the observed label, right, then basically what it means is that the model was very confident that the label should have been the opposite, right? It's very confident that the label should have been, say, plus, but it actually was minus. Right? In this case, this coefficient here is large, and you actually take a big step. Okay? On the other hand, if the model actually attaches a reasonably large probability of the observed label, then this quantity is smaller, right? And hence it is a smaller step. Okay, so it's a very natural step size. Does it make sense? Spell this out here, right? So this is large if model W is surprised by the observed label Y. Yeah, right? So it attached to y a very small probability. That means it touches a large probability to minus y, and hence takes a big step. Okay, and so then, right, so this is all we need in order to do gradient descent, or stochastic gradient descent, or mini-batch stochastic gradient descent, or its variance. Right, all the algorithms that we've discussed throughout this lecture. Right, so this is just vanilla SGD, stochastic gradient descent for this model, right? So we do the usual thing, right? So we iterate, pick a random data point uniformly from our data set, then we compute the probability of misclassification with respect to the current model, right? We compute the probability that y is minus y, right? The probability of misclassifying the current model, and then we take a step in the gradient direction weighted by that probability of misclassification. Okay, so that's gradient descent. And now, of course, if you do our stochastic gradient descent, if you do mini batches, you would not just pick one point, but the whole batch, right, and average the gradients. Okay, so it's a really intuitive algorithm. Okay, now this is basically just standard logistic regression, which is sort of the classification analog of least squares regression. and of course suffers from the same shortcomings, right? Especially if we have high-dimensional feature spaces and relatively little data, right? Try to fit high-degree polynomials from few data points, right? And so there's the danger of overfitting, and of course we can combat overfitting using regularization, right? The same ideas and arguments that we've used in the context of regression apply here just as well. Right? So effectively, all we've done is change the noise model, right? We swapped from a Gaussian noise to a Bernoulli noise. That's really the only thing that happened, right? And hence, similarly, it makes sense to consider regularization, right? And then, of course, we can use our standard toolbox of regularizers, right? We could do L2 regularization, which corresponds to Gaussian priors on the weights, or we could do L1 regularization that corresponds to Laplace prior on the weights, or other possible regularizers, right? And if we essentially match these, then essentially trying to solve this resulting regularized estimation problem or optimization problem is equivalent to doing Bayesian estimation, right? So you compute the maximum a posteriori estimate of your weight vector W just under this slightly different probabilistic model. Okay, and then of course you can do gradient descent on this regularized cost function, right? Using the same arguments, right? We already have computed the gradient of the regularizer, right? And that now just appears here the same way it did when doing, for example, gradient descent for ridge regression or gradient descent for the SVM, right? And so if you do L2 regularization, then that is the same as weight decay, right? Shrinking our weights towards zero, right? That comes out of the fact of computing the gradient of the Euclidean norm essentially just gives us something that's proportional to the vector. Okay, so this is basically stochastic gradient descent for L2 regularized logistic regression. Right, as the training algorithm. Right, so basically solving the learning problem for regularized logistic regression is essentially solving this optimization problem, for example, using stochastic gradient descent. And then, of course, we still have to decide how to classify it, right? So this is just learning, right? But then how do you do classification? Well, you do classification by looking at the conditional probabilities, right? So for a new test point that comes in, X, you compute this conditional distribution, right? The probability of each label for that point, and turn that into a decision. Okay? And so one natural thing to do is to just output the most likely label. Right? But we'll talk a bit more about how to turn these probabilistic models of our labels to discrete decisions actually in what's to come. Okay? But so one natural approach, just to mention here, right, would be to just say you estimate this conditional distribution of y given x in your model parameters, and that gives you a probability for each label, and you just predict the most likely label. Okay, so let's see a quick illustration of this. So this here is just running SGD on this data set. So here the solid squares and circles are the training data points, and the hollow circles and squares are the test data points. We can just run standard gradient descent, stochastic gradient descent for some iterations, right? And so here's what happens. This cross here shows the current data point that's randomly sampled, and it's the same kind of plots that you had seen before, right? What happens with the train loss and test loss, and of course you can use a larger batch size, so let's do that. Let's just, in this case, it's actually only 10 examples, so let's do the full batch. Which is actually just gradient descent on the cost function. And so this shows the algorithm. Now, what are the colors here? So the colors basically correspond to the label probabilities, right? The probabilities of the positive class. Okay, so the more red, the more likely red is, right? And the more blue, right? And this is something close to 1, this is something close to 0, and this is something in between. Okay, and so one thing you can that logistic regression tries to do is it actually tries to be careful about the label probability, right? It actually tries to model the probability of the positive or negative class. That's something that the support vector machine, for example, or the perceptron, does not try to do, right? So the SVM simply tries to make few mistakes, right? That's how we derived the hinge loss, right? As a surrogate for the 0-1 loss. We didn't actually try to somehow model the class probability well. Okay, versus logistic regression essentially tries to think about classification as estimating label noise, right? Estimating the label distribution, right? That's why these colors here now have a very natural interpretation, right? These are really the probabilities of each of these labels, right? And contour lines correspond to the contour lines of the class probability. Okay, so a few more remarks on logistic regression, right? This is, of course, sort of the most basic variant of the algorithm, right? And of course, you can apply all the other modifications that we've discussed before. So, for example, to go beyond linear models, you can look at nonlinear transforms to features. In particular, you can kernelize logistic regression. That's very straightforward. You can also go the neural network route, right? By instead of working with the features directly, you use feature functions that are parameterized through a neural network. And it's also very natural to extend to multi-class. And I just want to say a few words about each of these extensions, right? But this now really should be essentially clear how to do it, right? Using the standard machinery that we've discussed all through this class. Right? So here's kernelized logistic regression. And how do you get there? Well, you go the standard route that we've discussed all along. Right? We use the ansatz that our model is in the span of the data. This holds here just as well for logistic regression, right? So if you remember, right, so the same argument that we used, for example, for least squares or the SVM and so on still applies, of course, right? If you initialize with 0, then do gradient descent, you always move in the direction of your data points, right? That was derived, the gradient updates always go in the direction of y times x, right? They always construct models W that live in the span of the data. Okay, so this is the prerequisite that we have made use, right? That we have a particular form of our model W, right? Namely, the optimal solution W lives in the span of the data. And then you sort of manipulate the objective function to make sure that data points only appears in a product, replaced in a product by the kernel. Right? So, and if you go through that recipe that you've seen many times now, I'm not going to do it again, then you get to this form. Right? That's the same regularized logistic regression problem, but now after applying the kernel trick. Right? So here K is the kernel matrix. Right? And each Ki is one of the columns of this kernel matrix. Right? So Ki is just K of xi, x1, all the way up to K of xi, xn. Right? So this is how these always look like, right? And again, right, our optimization problem, now using this ansatz, right, of how the solution looks like, we can introduce these dual variables, right, these alphas. These are the coefficients in front of our data points. And so now we optimize over these alpha coefficients, right? So alpha is in Rn, we would have one of these variables per data point. Okay, so this is basically just, applying the standard machinery, right? The standard kernelization hammer that you've seen a few times now, just to this new optimization problem. And of course, you can make the same use for classification now, right? So now what this would give you is now you get a conditional distribution for each point x, okay, back. That's parameterized by our estimated alpha hats, right? And that is basically just 1 over 1 plus e to the minus w transpose x, spelling out what w is, right? Expanded in terms of the alphas. Right? And then you get the kind of function here, right? That you've seen many times, right? That's sort of a sum of kernel evaluations at the data points. So that's kernelized logistic regression, right? Just applying the same tricks and going through them again. Okay. Now, what about multi-class? So we already talked about multi-class in earlier lectures, so let's come back to this and revisit this in the context of logistic regression. And that's a very natural way to apply logistic regression in the case of multiple classes. Very much sort of in spirit of the multi-class support vector machine, right? Remember when we talked about multi-class classification, we had this one route that sort of looked at reductions, right, to multiple binary problems. And then we sort of looked at this problem where you optimize essentially all the classifiers together, right? And this is sort of this in the latter spirit. And the idea is basically that now instead of modeling a coin flip for the label, you model the outcome of a dice, right? So if Y can take, say, one of C many states, right? So C possible class labels, say 10 possible class labels, then we just try to model all of these probabilities together, right? We model the probability that Y takes label I, using continuous functions, very much in spirit of what logistic regression does. But now, of course, we cannot just look at one single number R that we pipe through the sigmoid, right? Because now we actually have to describe a probability distribution among C possible outcomes, right? And the way this is done in multi-class logistic regression is basically as follows. So what we're going to do is we maintain one weight vector per class, W1 up to WC, right? Remember, that's the same that we've done for, say, multi-class SVMs, right? We maintain one model per class, C of those, and they compete for each other, right? So they compete for the class label. Okay? And so the way they compete is that, so essentially each of them outputs the score, Wi transpose x, and we exponentiate that score. And now in order to get the probability, we just divide by the sum over all scores. Right? And that forces us to get a probability distribution back. Right? So this is pi hat, right? And then by construction, the sum over I of pi hat is 1. Right? So this is right, because we just make sure to normalize everything. Right? And that's just our model, right? So we replace this coin flip model by a dice throw model, right? By a categorical distribution instead of a Bernoulli variable. Right? And this now allows to model multiple outcomes, right? See possible different outcomes. Okay? And the model is parameterized in terms of the C weight vectors W, and now we can look at parameter estimation, right? Not just estimating one weight vector W, but C of them, right? By computing taking the log of this, right? Doing maximum likelihood estimation or map estimation, whatever we like, right? And so that technically would mean is we take the log of this likelihood, right? Sum this up, and this gives us our cost function, which you can optimize, right? And just have to compute the gradient and do gradient-based optimization. So one more thing I want to just mention here briefly is the following. So somehow doing multi-class logistic regression should just fall back to standard logistic regression in the case of two classes, right? And there seems to be a little discrepancy here, right? Here we say we actually maintain C possible weight vectors, one per class, right? But this would suggest if we have two classes only, then why shouldn't we be using two weight vectors for our two classes, right? W1 and W2, right? Remember in logistic regression, we just used one weight vector, okay? And so the key idea here is that this is actually a redundant parameterization, right? So the fact that we talk about the distribution, so the class probabilities need to sum to 1, essentially reduces the degrees of freedom that we have by 1. So we effectively really only have C minus 1 degrees of freedom. Okay, and we can enforce this by normalization. So let's spell this out. So the observation So if we take W1 transpose X, and now suppose we add a number, let's call it tau, divide by sum from j equals 1 through c of e to the wj transpose X plus tau. Right? So all we did is basically just shifted all the scores up by tau. Okay? But what does this mean? Well, this is a shift in the exponential domain, right? So we just take out that factor. So this is just e to the tau times e to the w1 wi transpose X divided by sum over j 1 through c of e to the tau wj transpose X, right? And now, of course, that just means that the tau cancels, right? So this whole thing is shift invariant. So if we shift the scores by some constant amount, it doesn't actually affect the distribution. Okay? So why is this relevant? Well, what we can do is we can just choose tau to be the score of one of the classes. Say class C, right? The last class, whatever. Okay? So can choose tau to be C minus WC transpose X. And why is this relevant? Well, in this case, essentially for the CF class, right? We just have e to the 0, right? Because the WC transpose X minus WC transpose X cancels. And that just gives us a 1 for the C, right? So it basically just fixes the score of one of the classes to 1. Okay? In this case, we really directly get back just standard logistic regression. It's a little bit of a technical point, right? But this is the connection. So it's a strict generalization of this logistic regression model that we had talked about before. Okay, so this is written down on the slide here. So basically what we do is we basically maintain one weight vector per class, but we can actually force one of these weight vectors to be 0, right? So really only optimize over W1 up to WC minus 1 if you have C classes, right? And the last one you just set to 0. Doesn't change anything about the resulting solution. And then basically you just do the typical maximum likelihood or maximum posteriori estimation, right? And this gives us a new loss function, right? The logistic loss. Now this is this multi-class logistic loss, and that multi-class logistic loss is also often referred to as the cross-entropy loss. I'll not explain where the name comes from, but that's sort of what is also often referred to in the literature. Okay, and this is a loss function that's extremely frequently used in neural nets. If you do multi-class classification with neural nets, it's the default loss function that's typically used. Okay, and so now the idea is instead of having a linear response, right? So each of these scores is a linear function. Now each of these scores is actually a non-linear function, right? That's given by a neural net. Right? So essentially you set up a neural net that predicts the scores for the C classes, F1 through FC, in the same way that we had discussed also this lecture, right? And now the loss function that you apply to the last layer is given by this cross-entropy loss. Right? It's just given by minus log of e to the fi divided by the sum of the fj. Okay, and this is differentiable. You can do gradient descent and so on. So this is sort of the standard way to do multi-class classification with neural nets. Not the only way. You could plug in the multi-class hinge loss as well. Or you could use a different encoding, as we had discussed, right, for the classes, and do a bunch of binary classifications per class label. Right? So certainly not the only way to do it, but that's the default standard. That's why I wanted to introduce it here. Okay? But it's basically just logistic regression, right? Only that you parameterize the features. right? Instead of going this kernelization route, now we go the neural network route and sort of explicitly, non-linearly parameterize our features. And then you optimize over the parameters used in those features using gradient descent. Okay, a few comparisons. There's a few things before the break, and then we'll do the break. So just a quick comparison between SVMs and logistic regression. Yeah, question?
I have a question. Sometimes we would like to have something that is entropy, that's like L1 norms. If we know that some features are not so.
Yeah. What do you mean, does this exist? So here for multi-class, right? So if some features don't exist, sure, you can do L1, right, on the weight vectors. And in fact, what you can do, and that's a sensible thing to do in this model, is to basically now use something called the group L1, where you basically want to make sure that you turn off. So essentially, you want to capture the fact that if you turn off the weight for one of these vectors, you turn it off for all the vectors. Okay, and there's the loss function. It's not the L1 loss, so you could use the L1 loss, but there's something different that would encourage this kind of group sparsity. Okay, so there's specific regularizers that capture this sort of structure. So it's a very good question, right? So the question was, can you enforce sparsity here as well if you do multi-class logistic regression? Absolutely. So happy to talk more in the break if you want. But it's a nice example of where you might actually use different regularizers than L2 or L1, right? So this is a good example for that. Okay, quick comparison, right? You've seen support vector machines, you've seen logistic regression. So which one you might want to use, or what's the relative merits? So they're really very similar in some sense, right? So you just have a different loss function, right? The hinge loss versus the logistic loss. And often in practice, if you just care about classification accuracy, they'll roughly do similar. There's many other choices that matter more. Okay, if you're really data starved, right, and you have few data points, maybe there's some difference, but in practice you won't see a huge difference between those. Okay, now that's right. So certainly for specific problems it could be different, right? But so in general they behave very similarly. Now that said, right? So with SVMs you directly optimize accuracy. You don't try to optimize the probabilities, the class probabilities, but the class label. Right? And sometimes that can lead to slightly higher accuracy, especially if you have little data compared to the number of parameters that you use. Okay, so the other advantage of the SVM is the fact that it, right, support vectors, so you get sparse solutions, right? So if you think about this, the kernelized SVM, the alphas, and so on, right, you tend to get sparse solutions. So for example, in the alphas, a lot of the alphas will be zero. But again, it's just sort of kernelized SVM. If you try to apply to really large problems, there's going to be problems anyways. Okay? So the sparsity and sometimes higher accuracy can be a benefit of using SVMs compared to logistic regression. The benefit of logistic regression is that you now actually model class probabilities, and quantifying this uncertainty in a class probability can be very useful. And we'll discuss some more reasons why going forward. Okay, and that's also the corresponding shortcomings of these methods, right? So for the SVM, it doesn't really correspond to a natural probabilistic model, right? So it does calculate some sort of confidences or scores, right? But they don't really have a statistical interpretation. So it's a bit, right? So there's various heuristics of how to calibrate and sort of turn SVM confidence scores into probabilities, but they're heuristics. Okay? On the other hand, logistic regression will lead to dense solutions, right? So the weights will be all non-zero, right? And sort of the alpha vectors will be typically all non-zero, right? Every data point matters somehow. Okay, so that's a bit of a comparison. Now, one thing I want to mention here, and I briefly had this before, but I just want to give this outlook because I think it's very useful, right? So we talked about this probabilistic perspective that comes out of this optimization based point of view towards supervised learning, right? So what we said is if you take this probabilistic modeling point of view, right, then essentially your goal is to really try to estimate the label distribution, right? If you can get your hands on the label distribution on P of y given x, then that's really great, right? You can make Bayes optimal decisions and so on, right? So that's sort of the best you can possibly hope for. Okay, of course, in practice with finite data, you'll never be able to actually do that, right? But you sort of try to estimate this distribution. And now there's different ways of doing that, of getting this conditional distribution, right? The distribution of the labels y given some point x. And so this optimization-based viewpoint, the first one, essentially posits a particular model, right, of y given x and w, and now finds a single, often called point estimate of the parameters, a single model, right? Say a single logistic regression, right, or a single linear regression model, right? So you get a single w hat using any of these optimization algorithms before. Apply a stochastic gradient descent to the map score function, for example. Right? That's what we've talked about all along. So essentially, the top part of the slide is what we've talked about essentially most lectures in this course. Right? So this should be very familiar. Right? So you would estimate a model w, and then you use it in order to make predictions. Right? You get your y given x and w, and say predicts the most likely label, right, or predict the mean or something like this, or the most likely, right? So this is sort of this top point of view. And now the bottom part of this slide here is an alternative to this, which we're not really discussing in this course, except this one slide. I still want to bring it up because it points to a very important part of predictive modeling that we will not discuss here, but you should know that it exists, okay? And the idea here is that instead of just committing to a single solution, you actually maintain uncertainty about the solutions, okay? So, and the point of view comes essentially from this Bayesian perspective, right? We've seen that regularized estimation, right, rich regression, regularized logistic regression, etc., right? It can be viewed from essentially the Bayesian point of view of finding parameters that are most likely a posteriori, right? Taking a prior and the data into account. Okay? But now the point is that this distribution of W, so this distribution here, right, is actually a full distribution in principle, right? If you take this Bayesian viewpoint seriously, right? It just maybe says one of the models is maybe the most likely, but there's many others that could also plausibly be explained by the data. Right? And now you can ask, well, why should I collapse all my uncertainty, right? Why should I just commit to a single model? Why not use all the models weighted by their probability somehow, right? And this is what's done in Bayesian learning or Bayesian modeling, model averaging, right? So instead of optimizing over P of W given X, P of W given the data, you integrate with respect to W given the data. So you look at all possible models of W and average their predictions weighted by how much the data supports these models. Okay, so it means there's no optimization. Right? That's really fundamentally a different approach, right? So instead of doing everything here has been optimization centric. Okay? So this Bayesian viewpoint says forget about optimization, all I need to do is integration. Okay? At least conceptually. Right? So it's philosophically a very different kind of approach, right? That's why I want to bring it up here. Okay? And now why is this useful potentially? Well, it can be very useful because it quantifies the uncertainty. It actually not just looks at one model, but it looks at all models, at least that you consider under your prior, and you average according to how likely they are. Right? So this uncertainty can be very useful in certain applications. But of course, the issue is that now you have to do integration instead of optimization. And in general, integration is a lot harder than optimization. Okay? And now one has to talk a lot about different classes of approaches that sort of try to solve this integral approximately in some form or the other. And that we will not cover here, right? I just wanted to have this one slide as an outlook, right, to mention these kinds of approaches. Okay. So to sum up our big picture here, right? So this is, we started with least squares regression. And then what we said is least squares regression, if you basically regularize, you get ridge regression, right? And now if we to go to classification, right? Now going from least squares regression to logistic regression is just swapping the likelihood function or the noise model, right? Going from Gaussian noise to Bernoulli noise, coin flips, right? And then we can just as well, using a prior, to get to regularized logistic regression, right? So this kind of commutative diagram that you've seen before. Okay? We can kernelize either of these things. We worked out what is kernelized linear regression, right? And I showed on one slide what is kernelized logistic regression, right? The derivation is basically the same. It's very similar. Okay? And now, this, with regard to the just previous slide, right? So now you can also, instead of just getting this point estimates, a single solution via optimization, you can average over all solutions. So you can do this Bayesian model averaging. And this leads to what's called Bayesian linear regression. That's sort of the model averaging version of rigid regression. It's called Bayesian linear regression. And you can kernelize this and get to Gaussian process regression. And that's a very widely used, very effective class of Bayesian learning methods. Okay? And you can go the same route in the classification world, right? You can apply Bayesian model averaging to get to Bayesian logistic regression, and then you can apply kernels to get to Gaussian process classification. Okay? And now you can also go, and that doesn't fit on the slide here, right? But you can go the neural network route, right? To non-linearly parameterize the features both for classification and for regression. And you can even do Bayesian model averaging in the context of neural nets, right? And there's quite a bit of work on Bayesian deep learning, for example, right? So trying to quantify the uncertainty in neural nets. Okay, but we'll not discuss this in this course here. Okay, and also this slide here, just to add to it, right? So what's new here in blue, right? So instead of this optimization or objective, we now sort of have this additional interpretation of basically the same thing, right? So now this is, you can either take this optimization-centric perspective or this probabilistic perspective, right? And on the latter, the loss function gets replaced by the likelihood, and the regularizer gets replaced by the prior. Right? And now we've seen these correspondences, so square loss is equal to Gaussian likelihood, logistic loss is equal to the Bernoulli likelihood, cross-entropy loss is equal to the categorical likelihood. Okay, sort of this loss versus likelihood point of view. Similarly for the prior, right, L2 norm is the Gaussian prior, versus L1 norm is the Laplace prior. Now in terms of methods, right, I just added Bayesian model averaging here, right, as a different learning method that actually would now not optimize but integrate, but have it in gray because we didn't really discuss it here. Evaluation metric, right, of course now, since you talk about likelihoods and so on, you can actually look at likelihoods of your model on a test set. Right, so it's a metric that has a natural interpretation now on the test set as well. Right, and of course also even for model selection, turns out this Bayesian viewpoint can be very useful. And so it turns out one can, in some cases, gives you an alternative to things like cross-validation. As I said, we won't discuss it here. So let's take the break now. And what we'll do after the break is we'll look a bit more at this question of once we have this probabilistic model, how can we use it to make decisions? So let's talk about this after the break. Okay, so what we've seen in the last lectures and the first part of today's lecture is how we can view a large part of supervised learning as the problem of estimating a conditional distribution over our labels given our inputs. Right, so both regression, classification, we can view this way, right? So essentially, you can view these problems as trying to estimate models of P of y given x, and some model parameters that we would try to estimate. But what we haven't talked too much about is what we can make use. How can we use these conditional distributions? And what I want to talk a bit more about in the following is how we can use these estimated conditional distributions in order to make decisions. Okay, and so one of the goals will be to rederive or get a justification of the kind of prediction rules that we've been using, like predicting W transpose X for regression or sign of W transpose X for classification. Those seem somewhat arbitrary, right? We want to sort of see if they have a natural justification from this viewpoint. But we also want to see how estimating these conditional distributions can be used and be useful beyond these basic decision problems that arise in regression and classification. So that's the plan. And so let's start with a simple example, just to illustrate things, and then we'll generalize. And so the idea is as follows. Namely, let's go back to our spam filtering example. Right, so we want to build a system that filters incoming email messages. In particular, that takes one out of three actions. So either it sends an incoming email message into the spam folder, it sends it to the inbox, or it sends it to the inbox but highlights it, right? Somehow asks the users, please take a look at this specific email. It might be spam or not. Okay, so let's just think about having these three possible outcomes, or three possible actions that you might take in our system. Okay, and now, of course, as training data, all we have is, say, a bunch of email messages that are labeled as spam or not spam. Right, so our data set is the typical classification kind of data, right, where we have email messages X labeled as spam, yes or no, so it's just binary classification. Right, so let's apply the logistic regression. So suppose we estimate this conditional distribution of basically of the probability of Y being spam given some input X. Okay, and let's call this, just refer to this as little p, right, this number between 0 and 1. Okay, and now the question is sort of how should we, right? So now essentially in our training data we only have these two possible labels, right? And we estimate a distribution only over these two possible labels, spam or not spam. But we want to take one of these three possible decisions, right? Spam, not spam, or ask user. Okay. So now the question is how should we go about doing this, right? Making this decision in sort of a principled manner. And one way to view this is to essentially do a case analysis, right? To sort of think about what is the consequence of taking an action in a certain state, right? In case of a certain label, right? So if the incoming message is a spam message, what would happen under each of our three actions? And somehow quantify the consequence of that action, right? Using some notion of cost. Right? You can try to work out and also specify a little table that looks like this. So here we have our actions. Right, so I just mark these letters S, N, and A, right, for spam, not spam, and ask user, N and A. So these are the actions we can take. And then we have the different cases, right, so the labels, right, so Y equals spam, or Y equals not spam. Right? And we can try to work out what is the cost, or specify what is the cost in each of these cases. Right? I can think of it as a negative utility. Right? So let's say if we classify it correctly, we have 0 cost. Right? So we ideally want to say spam if it's really spam, or say not spam if it's not spam. But then we can think about the cost in each of these other cases. Right? So, for example, if it's actually not a spam message and we do send it to the spam folder, right, it's possibly really problematic, right, for reasons that we discussed quite a bit in this course. So let's attach a high cost, say 10 units of cost. Okay? And similarly, if it's actually a spam message, but we declare it as non-spam, so send it to the inbox, we get maybe 1 unit of cost. And now if we ask the user, no matter what we do, we incur some cost. Right? Because somehow the user, it's inconvenient for the user, right, to somehow be interrupted, right, and being asked about one particular email, right? And of course, it's a stylized application, right? But so suppose this has cost 0.5, right? Now, if you knew the true label, then of course we knew which action has the lowest cost, right? So if you knew it's right, it's spam or not spam, we would just take that action. That's clearly the lowest cost action. But the problem, of course, is we don't know. All right? All we have is the estimate of the uncertainty in the label y. Right? And now the question is, how can we actually take this richer information, namely this probabilistic information, right, the estimate of P of y given x, in order to turn it into one of these decisions, right? And intuitively, sort of what you might want, right, is that if you're really confident about the true outcome, right, if you have a very confidence either true or not spam, right, spam or not spam, you would take that corresponding action. But maybe if you're unsure in the middle, maybe you want to ask, right? That's the intuition. But of course, now the question is, how should you make this decision, right? And one way to do this is to not look at the cost, but look at the expected costs according to this distribution, right? So we can look at the expected costs of each action. Right, C and A for different values of P. Right now, this really depends on each possible realization of this probability P, which is not a binary label, but actually a number, right, from 0 to 1. Okay, and so let's just look at two concrete instances, right? Say 0.2 or 0.8, right? So you can try to work out what is that expected cost in each of these cases, right? And so in the case that P equals 0.2, right? So the probability of spam is very small, right? Then what's the expected cost? It's 0.2 times 0 plus 0.8 times 10, right? That's 8. Right? In this case here, right? If we say we take the action not spam, we would suffer 1 unit of cost in 20% of the cases, but 0 in these other cases, right? And here, of course, doesn't matter what state it really is. We suffer 0.5, right? And so the action that minimizes the expected cost would be to just say not spam, right? So that's the one that minimizes the expected cost. Versus if we just do the opposite here, right? 0.8 times 0 plus 0.2 times 10 is 2. 0.8 times 1 plus 0.2 times 0 is 0.8. And here it's 0.5, right? And so now the lowest cost action is actually the ask user action, right? So in this case here, essentially, if we think the probability of the spam is very small, right, then we really want to send it to the inbox without asking the user. But with the flip probability, right, 80%, if you think about 80% spam, then we're maybe not confident enough, right, to just send it to the spam folder, but rather ask the user instead. Okay, so that's sort of the idea of how you can actually take, even though you just have this binary classification problem, right, spam versus not spam, how can you use richer information, maybe this conditional distribution, right, the probability of the class label, to actually take a richer decision. Okay, so that's a motivating example, right, of thinking about decision making, right, in this probabilistic setting a bit more generally. And this is what's modeled in the context of Bayesian decision theory. Yeah?
Sorry, I'm confused. Is that the probability that our model will predict this?
Yeah, so suppose we know the true probability, right? So so we haven't said anything about model the actual probability, right? So suppose we did a good job at fitting our logistic regression model. Absolutely, right? Now, of course, that might be wrong, right? And we can sort of study the consequences of that. But for now, right, let's separate these concerns. Right? Before we talked about how to estimate this conditional probability, now what I want to convey that it's actually useful if we could do so, right, for various purposes. Okay? yeah, then you have to break ties somehow, right? If the cost is the same, then it wouldn't. You'd have to arbitrarily make that decision, right? Right. So. Right, and so this is basically the more general setup of what's called Bayesian decision theory, right? Where we work with conditional distributions over labels, right? A P of y given x, say coming out of logistic regression, for example, right? Where we have a binary label. This could come out of multi-class logistic regression, right? A categorical distribution over C classes. Or this could just be our standard linear regression, where this is, say, a Gaussian distribution, right? All of these models would fit this here. And we'll work through some of these examples later. Right, so y is the set of labels. E.g. +1, -1, R for classification, 1 through C, etc. Right, so this could be any of these settings that we've discussed. And then we have our set of actions. And we have a cost function, right, that looks at the consequence of taking an action under a given condition, right, and a given true label, right? And so now here, as the previous example showed, it makes a lot of sense to consider settings where y is actually different from a, right? So it could be that that a is not equal to y, right? So the action set might be different from the label set, right? And the example before I already showed one example. And now what Bayesian decision theory recommends is to pick the action that minimizes the expected cost. Okay, so this is what we worked out before, right? So basically, it would recommend to pick the action A star that minimizes over all actions A, the one that has lowest conditional, the lowest costs in conditional expectation given x, right? So you look at the conditional expectation over the cost of that action, taking the uncertainty about the label into account, right? So basically, for classification, right, in the discrete case, this might be, say, the sum over y of the probability of y given x of c of y comma a, right? So what we had on the previous slide. Okay, and now if we really had, and this gets back to your point, so basically if we had the true distribution p of y given x, then that resulting decision is called the Bayesian optimal decision. Okay, now in practice we'll never be able to perfectly estimate p of y given x, right? But what we've talked about, essentially everything we've tried to do is to try to get close, right? To try to get some sort of hopefully accurate estimate of p of y given x. Right? So for now, let's assume that we actually have that distribution, right? And work on that assumption. Right? And of course, if it's not true, we can try to estimate the consequence of misestimation, right? Of this conditional distribution on the resulting actions. Okay? So let's work this out in the context of logistic regression, right? So what we've talked about in the first part of today's lecture, right? So which is this Bernoulli noise model. We model a Bernoulli coin flip distribution. So what are basically, how does this fit this framework here? So we estimate our conditional distribution, right? P of y given x is Bernoulli. Right, I'm omitting the parameters here, right? Because we really only talk about this conditional distribution of Bernoulli distribution evaluated at y with bias that's given by the sigmoid function applied to W transpose x, right? Or say a neural network evaluated at x and then piped to the sigmoid function. Okay, and now our action set is really just +1 - 1. We want to estimate the class label. And now a natural cost function to look at here is the 0, 1 loss. Okay, so let's look at the 0, 1 loss, which is just the indicator of whether y agrees with A. Okay, so let's look at the setup, right? So we use as our model a Bernoulli model, right? So we have a Bernoulli distribution, right, of y over y. Our action set is +1 - 1. And our cost function, right, so applying a cost under a given label is just a cost of 1 if you got it wrong, and a cost of if you got it wrong, and 0 if you got it right? So it's just a 0, 1 cost. Okay? And now we can ask, under this particular cost function, how should we convert this probabilistic distribution over y to a single action? Right, so let's just work this out formally. Right, so the cost expectation with respect to y, so y is random for a given action A conditioned on x. What is this? Well, this is just the sum over labels y of the probability given x times the cost function, just plugging in, right? And now what is this? So this is basically just, if you work it out, right, it's just the probability that y disagrees with little a under our model. Right? So this is just what happens if you work out what is this conditional expectation. Right? It's the probability of misclassification. And so what is this? Well, this is just 1 over 1 plus e to the a times w transpose x. Why is that? Well, the probability of the label y is right, 1 over 1 plus e to the minus y times w transpose x. And if I plug in y equals minus a, right, the flipped label, a misclassification, I just get e to the a times w transpose x, right? Okay. So now what's the optimal action? So a star, right, so in the argmax over a and +1 - 1 of this quantity here, sorry, argmin, we want to minimize the expected cost, right? Argmin of right, this argmin of this ratio, that of course is just argmax of the denominator, right? Argmax of a +1 - 1 of 1 plus, let me just be very verbose here, right? A times w transpose x, right? Which is of course just argmax over a of a times w transpose x, right? Because the 1 plus e to the something is monotone, right? And now if we solve this optimization problem, right, where a is just this binary variable +1 - 1, what do we get for our a? Well, we just pick the same sign, right? So this is just the sign of w transpose x, okay, which shouldn't be a surprise, right? So this is sort of a justification of why we sort of would classify with sign of w transpose x, right? So you can view it as sort of a consequence of applying this framework, right? This Bayesian decision theory, right? With the actions just being the predicted labels, and the cost that you want to minimize is this misclassification cost, right? So basically just the 0, 1 loss. So similarly, right, so sort of justifying or viewing or interpreting the least squares cost as a Gaussian likelihood, right, or the squared weights as a Gaussian prior, we can now sort of interpret the sign of W transpose X as trying to find an optimal decision under this conditional distribution, under this particular cost model. That's the purpose of this slide, right? This is a very convoluted derivation here. It should be very obvious that that's the right thing to do, right? But this is sort of how it's out of this framework. Okay? So that's a single principle, right, that allows you to derive this. Okay? So this is just spelling out in LaTeX what we just derived in the previous slide, right? So basically, the action minimizes the expected cost under the 0-1 cost. And this Bernoulli noise model is just sign of W transpose X. Okay? Starting point, right? But now we could say, well, what happens if we plug in different losses, right? Different costs, or we have different action sets, right? Similarly, right, to swapping likelihoods or swapping priors, we can now sort of swap different decision problems and see what happens. Right? And so here's a natural one that relates to what things we've discussed earlier in this course. But now connecting to this probabilistic viewpoint, well, so what if you have asymmetric costs, right? False positives are more expensive than false negatives. Right? So very simple to model. So again, we have the same conditional distribution of y given x. Our action set, again, is just predicting the label, +1, -1. But now, instead of the 0-1 loss, we have an asymmetric cost function. Right? We spell out what is the cost of a false positive versus cost of a false negative. Right? And so basically, what we can now do is we can calculate the costs that we would get when predicting +1. Right? So what is this? So it's the so this is the cost of predicting plus. Again over y, right? So what is this? So this is so if you predict plus and the true label is actually plus, then we get 0 cost, right? But if we predict plus and the true label is minus, right? Then we have CFP, right? Times the probability of y equals +1 given x, right? So this is the probability, -1. Right, this is a false positive, right? Okay, something wrong, no? Okay. And so let's say, if we again use this convention, right, that little p is probability of y equals +1 given x, then this is CFP times 1 minus p, right? Okay, and similarly, C minus is the expected cost of y, of basically taking the -1 action. So it's false negative times the probability that y is actually plus. Is CFN times p, right? And now, what does it mean? Well, we would basically predict +1 if and only if C plus is less than C minus. Or we could decide how to break ties otherwise, right? But so we break ties this way. right? And now let's solve this for p, right? So what has to hold for p? So I have, okay, so let's see. P, so I'll put, okay, so we have CFP divided by CFP plus CFN, right? I hope this is correct, right? So we take P times CFP to the side here, right? And then divide by C of Fn plus Fp, right? Okay, so what does this mean? So, and here this has to be greater than equal to, right? Okay, and so what does this mean now? Well, if false positives and false negatives are the same, right, then obviously this just means we compare with a half, right? So we just compute the probability and see if it's bigger than half, we would predict positive. But now if CFP is bigger than CFN, right, if the cost of false positives is higher, right, than the cost of false negatives, then this ratio here is bigger than a half. That means we apply a higher threshold, right? We want our probability to be bigger than 0.5, right? And then that means we this is sort of the way to minimize our costs. Okay? So basically, you naturally derive this decision rule out of this setup here. Okay, so here's just a little illustration of this, right? We basically have, depending on how you set this threshold between false positives, false negatives, you shift around the decision boundary, right? So according to this threshold, right? And it's the same kind of threshold that you've seen when discussing cost-sensitive classifiers earlier in this class, right? But now motivated from this probabilistic standpoint. Okay, there's other things one can do. Let's just briefly mention those. So for example, what you could do is you could say, this is sort of this ask the user kind of idea that we had discussed before, right? So suppose you can take 3 actions, right? You can say either positive, negative label, or I don't know, right? So there's a don't know action, right? And now what's your cost? Well, your cost might be just a 0-1 loss. So you get 1 unit of loss if you got it wrong, 0 if you got it right and you made a decision, and you get some fixed amount of cost C if you ask, right? Or if you declare that you don't know, right? And then you can still work through that same kind of analysis, right? And it'll tell you that the optimal action is now to basically compare the probability, right? So look at your confidence in your label, right? Check the probability of y given x. And if this is bigger than 1 minus c, you would predict the label. And if it's less than this level c, you would just say, I have no idea. Okay? It just sort of naturally comes out of this, this viewpoint, right? So here's again sort of an illustration where this here in the middle is basically where you doubt, right? Where you would put the output the don't know action. Okay, and so this just very naturally falls out of this viewpoint, right? So this is sort of to convey that this conditional distribution is really valuable, right? So not just contains the label, but quantifying the uncertainty in this label is extremely useful if you later on want to make decisions based on this estimated model, right? That's why I wanted to emphasize that quantifying the uncertainty in a prediction, so not just predict the label, but quantifying the uncertainty in that prediction is extremely useful. Okay, so you can do similar things in the context of regression as well, but given that we're out of time, let's finish that discussion in the next lecture, and then we'll actually start a new topic that opens another perspective on learning, namely going from discriminative to generative modeling. Okay, we'll talk more next week.